Hi, everyone. Welcome. I'm Suresh. I'm a product manager for Amazon Aurora. And for those of you who are not familiar with the service, Aurora is a fully managed MySQL and Postgres-compatible database that offers the performance and availability of a high-end commercial system, along with the cost and simplicity of open source. It's my real pleasure today to introduce Zhenya Hu and Ruben Lee from Airbnb. Airbnb is a longtime user of RDS MySQL, which they've used to power most of their production workloads. And as their business has scaled, they were looking for something that was even more performant, even more available. And they've chosen Aurora. As I worked with the team through this migration process, one of the things that really stood out to me is the world-class infrastructure that they've put in place to test and migrate web-scale workloads. So without further ado, Zhenya Hu to describe the journey to Aurora.
Hello, everyone. This is Xingyao and Robin from Airbnb's infrastructure team. Today, we are going to give a talk on how we migrate our databases to Aurora. The agenda of the talk are the following. First, we are going to briefly introduce Airbnb's architecture. We will go over our database setups in depth, and we will illustrate the challenges we have seen in the past few years, both from the nature traffic growth and the increasing number of engineers. These challenges become the motivation for us to test and adopt better databases technologies. We will explain how do we test and benchmark Aurora to make sure that it will meet our production needs. In the end, we will introduce our migration approaches to migrate to Aurora with minimal site downtime. Let's start. For those of you who are not familiar with Airbnb, Airbnb is an online marketplace for hospitality services, enabling people to lease or rent short-term lodging, including vacation rentals, apartment rentals, and so on. It has over 3 million listings distributed in 65,000 cities in 191 countries. Let's first briefly look at Airbnb's architecture. A few years ago, Airbnb starts with a very simple architecture, three-layer architecture. The request hit our load balancer and gets forwarded to our web server. We choose Ruby on Rails as our web framework, and our most critical data are stored in MySQL. We partition the databases by product features. For instance, all Airbnb messages are stored in MySQL databases named MessageDB. All listing availability information are stored in databases called CalendarDB. The most critical data, such as reservations, are stored in our main databases we call AirMaster. We run MySQL entirely on Amazon RDS. In order to support more re-QPS, we start to run multiple RDS re-replicas. Typical cluster would consist of one master and up to 10 re-replicas. A few years ago, we decided to move away from this monolithic Ruby on Rails architecture to a more service-oriented architecture. Services like search and risk has already been running on standalone Java services, and there are ongoing migration to pull the rest services like pricing and payments into separate services. We use open source software extensively in various kinds of stacks. For instance, we're using Nginx in our load balancer. We're using Zookeeper to power order service discovery. We're using Elk to store and query production logs. In addition to MySQL, we use Redis and Memcache to store ephemeral data. So what is the business requirement on the database side? So for a typical page on Airbnb, for instance, the listing detail pages, it takes the web tier will query databases from 30 to 50 times. And every single query would take, on average, 1 to 2 milliseconds. And P95 latency would take about 10 milliseconds. So any small regressions and issues on the database side can be very easily observed from our web tier. From a database's cluster point of view, the biggest clusters we get take over 100,000 QPS. So here's a summary of our databases deployment. Mostly using MySQL, we have very few Postgres and Oracle. These Postgres and Oracle are used by vendor software or third-party software who has very strong dependencies to these databases. We were running MySQL on EC2 initially. It was a challenge back in 2011. It was a challenge for us to implement the proper automations to run MySQL on EC2. For instance, all the massive failover, backup, restore, and PITR. Back in 2011, we made a decision to migrate all our MySQL databases to RDS MySQL, and we are 100% running on RDS MySQL since then. Up until right now, we have hundreds of RDS clusters deployed. We're also using Terraform to manage all the databases. The benefits of using Terraform is that all the changes to our databases cluster is version controlled and peer reviewed. Let's go over some of the challenges we have experienced on the databases layer in the past few years. The first challenge is to support Airbnb's fast business growth. This graph shows how weekly traffic count and response time changes in the past 2 years. The red bar represents the aggregated weekly traffic counts, and the red line represented the average response time observed on web layer. You can see very clearly that the traffic to Airbnb grows very quickly, while the user experiences does not degrade in the past 2 years. So on the back end, we have done numerous optimizations, such as caching, reducing unnecessary databases query to support the business growth. However, given all the optimization implemented, it becomes harder and harder for us to achieve the same year over year. Therefore, we are actively looking for new databases technologies to help us scale the site. The second challenge is introduced by SOA initiative. With the transition to SOA, more engineers are building services. Now we have hundreds of services and hundreds of databases clusters running in production. The increasing number of databases clusters make it really hard for us to provision, modify, monitor, and operate databases. In the next few slides, I'm going to explain how jitter impacts our site availability and how the increasing number of clusters make the problem worse. Another issue we are seeing is fast data growth. This graph shows the free space percentage changes on one of our critical payments databases. You can see clearly that the client is inserting a lot of data, and in the past few months, we have increasing the EBS volume on the underlying RDS instances 3 times, and it is provisioned at the maximum capacity right now. According to our estimation, it's going to run out of disk in about 5 months if nothing is being done on the application side. One way to solve this is build sharded MySQL. On the application layer, the idea is that try to distribute data to more than 1 RDS instances. However, it's pretty challenging for us to finish this within 5 months, given all the complexity of dependencies on databases in Airbnb's infrastructure ecosystems. Over the past few years, we have observed a few challenges while running at web scale. The first challenge is that it took more than a day for us to create a replica for some of our bigger databases cluster. For instance, this is especially inconvenient when we want to expand our replica during a spike of user traffic, for instance, during the Super Bowl ads time. A similar issue is that it took about a similar amount of time to restore a databases for some of the big clusters. Restoring a databases is a fairly regular process for us. For instance, we use databases backup and restore to move data from our databases to the data warehouses. In addition to that, we restore databases to run experiment to tune and benchmark MySQL configuration changes. The additional 16 hours of delay is acceptable for some of these use cases. Another issue we observed is while restoring databases, it's often needed to warm up the instances. Applications often see significantly more latency after the instance is initially created. Therefore, we have built a customized script to warm up the instances by scanning every single row on databases. This entire process takes several hours, and it's quite inconvenient for us. The last challenge we see is frequent jitter. This graph shows the effect of jitter. When it happens, we see constant read-write latency increase on the RDS instances. As a result, MySQL threads running increase on the RDS side. Then from the application point of view, the read-write latency to databases will increase, and maybe the application will start to see timeout, and the users will see 500 pages. On a per instance level, it might appear only a few times in a year randomly. The length of jitters vary from a couple of minutes to a couple of hours, depending on the underlying events on the Amazon side, which we do not have a lot of visibilities into. This is a failure scenario where we have very little controls on our side. From a single instance point of view, it might not seem to have a big deal if there's only a few jitters happens in a year. However, if you look at the aggregated level, it is quite concerning. This is a graph shows the effect of jitters on a small portions of our production databases. Each line represents a database with a different color. You can see clearly that in this 4 hours period of time, jitter is constantly happening. In order to alleviate this, we have implemented a few fallback strategies in our databases client and proxy. For instance, our client would automatically retry the query if the query times out on a database's replica with jitter. However, if the issue happens on master, there's very little we can do. According to our estimations, about 10% of Airbnb's downtime can be attributed to latency jitters. The current Airbnb's availability metrics is somewhere around 3 to 4 nines. 10% is a small number, but we still want to optimizing it. The jitter problem is enlarged by our critical business flow depends on more databases, which is the problem when we're running at web scale. Because of all these challenges, we start to consider alternative. By the time we do evaluation, there are two alternatives to us. One is EC2 MySQL. The second is Aurora. The benefits of running EC2 MySQL is that we get access to underlying local SSD directly, which is more performant. Also, we have more control and visibility into the system. We could have SSH to the instances and does an instance level profiling. The downside is that we need to staff a DBA team and starting working on a lot of the automation pieces where RDS MySQL already provides, such as databases backup, restore, point-in-time restore, and creating replicas. And also, due to the limitations on a single dependency on a single EC2 instance, we need to handle the sharding in the database sharding in the very near term. On the Aurora side, Aurora solves a lot of the problems we see in the past. No jitters, can scale up to 64 terabytes. In terms of the operation, it is very similar as RDS MySQL, which we already get used to. And also, we are really excited about some of the features, Aurora features, which is not available in the standard MySQL build. Given all of this, we decided to evaluating Aurora first. In order to evaluating Aurora, we build up evaluation metrics, which can be categorized into 4 different buckets: performance, compatibility, failure scenario, and operational overhead. In performance, we were first evaluating latency, meaning that given the same production workload, Aurora needs to be on par or faster compared with RDS MySQL. We also evaluating the throughput. The definitions of throughput is that given a latency threshold, how much more QPS can Aurora take in terms of read and writes. In the compatibility sessions, we want to making sure that from our client, Ruby and Java client point of view, Aurora is no different than a normal MySQL instances. We also studied transaction isolations in the hope that all the existing databases transaction will have the same semantic as before. We also tested it durability setting, meaning that during a massive failover, Aurora do not lose more data compared with RDS MySQL. We also have a lot of tooling built around MySQL. For instance, we use MySQL bin log to do change capture system to send the MySQL bin log into the rest of Airbnb's infrastructure. In addition to that, we have monitor script to pull InnoDB stats and sending these monitoring metrics into our monitoring systems. In addition to that, we use extensively MyDumper, MyLoader to do logical databases backup. We hope all of these tools will still work. In addition to that, we studied a lot of failure scenarios, which we often commonly see in RDS MySQL. Take master failover, for example. We want to calculate how long does it take for both Aurora and RDS MySQL perform master failover. In the last section, operational overhead, we study the most common operations we do. For instance, create cluster, create re-replicas, and doing point-in-time recover in the hope that on the operational side, Aurora will perform much better. Now I'm going to hand over to Robin to cover the rest of the sections.
Hello, everyone. Can you hear me? Hello, everyone. My name is Robin Lee. I'm a software engineer working on the Aurora migration. So I'm going to talk about some of the technical details on how we evaluate and migrate Aurora. So what we care most about is the Aurora's performance. For performance testing, we use a tool called DB-Replay. DB-Replay is an in-house developed load testing framework. It's a tool to test against production workload without actually putting your DB into production. So we can use DB-Replay to stress test the database with 1x to 10x workload. In the past, it helped us to do a database headroom projection. And right now, we are also using it to verify new infrastructure projects like the Aurora migration. So this is the high-level overview of the DB-Replay. So in production, we have front-end applications sending queries to the production databases. At the same time, they are also logging the actual SQL queries they made to a database, to the Kafka queue. We have a daily job to restore the instances from production databases, backups. And those instances will be used to test against DB-Replay. To start a DB-Replay test, we go to the DB-Replay controller web application and create a test job. The test job will spawn multiple DB-Replay workers depending on how many times of production workload we want to replay. And the workers will consume events from the Kafka queue and get the SQL queries out of it, and then send the queries to the DB-Replay instances we want to test. While the job is running, we can monitor the performance using CloudWatch and MySQL metrics from our Datadog dashboard. So this is the UI of DB-Replay, just to give you an idea of how it looks like. First of all, you can specify the source database workload you want to replay, and then the target database host name you want to replay the workload on. And then you can provide the starting, incremental, and ending load multiplier. For example, you can just put starting load 1x, starting load as 1, incremental load 0.01 per minute, and ending load 4. And then you put the duration of the test, and finally you can say replay the queries start from the given timestamp. We tested one of our write-heavy workload using DB-Replay, and here is how we compare MySQL and Aurora side by side. The blue line represents Aurora, and the purple line represents MySQL 5.7. We ran 4 times of production workload, which is around 30,000 QPS. And the yellow dashed line was the current production workload, which is near 8,000 QPS. Both Aurora and MySQL were running on R3 AX large instances, and the MySQL instance has the max out IOPS settings. We are sending the same QPS to both instances. If you look at the total QPS graph on the upper left, the 2 lines actually overlaps, which means they are getting the same amount of traffic. However, on the right-hand side, you can see that Aurora performed much better in terms of client-side read-write latency. Here's the performance metric summary we got from the write-heavy load tests. We saw Aurora has 2 times of read headroom and 4 times of write headroom compared to RDS MySQL. The headroom the term headroom here means that the maximum throughput we can achieve while keeping the latency within our SLA. And under the same throughput, Aurora's write latency is 75% lower than MySQL. Please note that these numbers are only for the specific workload we are testing. You may see different results for your specific workload. And we also did a lot of non-performance testings. Here's the test summary. We verified that Aurora is fully compatible with our Ruby client and JDBC. And it has the same transaction isolation behavior as MySQL. In a crash event, Aurora does not lose any bin log. And it also provides comparable CloudWatch and MySQL metrics as RDS MySQL. Aurora is fully compatible with some of the common toolings we are using, such as MySQL binlog, MyDumper, and Terraform. During the evaluation, we didn't observe any network blips. And for one of our largest database cluster, the time to do a master failover went down from 2 minutes to 20 seconds. And the time to create a re-replica went down from 1 day to 5 minutes. And the time to do a point-in-time restore went down from 10 hours to 1 hour. Another nice property about PITR, Aurora's PITR, is that it does, the restore instance reach the maximum performance immediately, and we don't need to do a warm up like the EBS. Before we started the full-scale migration, we want to put Aurora into production with relatively low risk, and we decided to use Aurora re-replicas to serve read traffic. We ran Aurora re-replicas on our biggest database clusters for a month just to test its stability in the real production environment. We observed no jitter during the Aurora evaluation. This is a big win for us because that means by switching to Aurora, we can eliminate 10% of our total downtime. Now let me talk about actual migration. So we have some high-level requirements for the migration. First of all, migration should minimize disruptions on end users and our product teams. A few months ago, we finished a project to migrate RDS instances into VPC. We used to take down the whole site for 20 minutes of maintenance, and then fail over dozens of clusters at the same time. This is a highly risky, error-prone, stressful operation, and was not a great experience for everyone involved. At this time, for the Aurora migration, we want to do something better. Secondly, the migration should be scalable enough to handle 100+ clusters. The migration should have a well-defined process and should be automated in most parts, simply because there are so many work to do. And finally, the migration should be reroutable. We want to have a way to fall back to RDS, MySQL, if anything goes wrong. Let me share with you our migration timeline. We started the Aurora evaluation on July 2017. And then in September, we finished the evaluation, and we started to run Aurora re-replicas in production. In October, we migrated a few most important masters to Aurora to test the failover process while still keeping the RDS MySQL fleet. At this time, we can still revert the migration if necessary. In December, we are going to failover all the masters while keeping the RDS MySQL fleet. We will run it for a month, and if everything goes well, we will gradually start deleting all our RDS MySQL instances. Since we have 100+ clusters to migrate, we need a scalable way to manage those RDS instances. At Airbnb, we use Terraform to manage RDS resource with code. The right-hand side is the code that describes one of our biggest Aurora clusters. The code describes the cluster with 1 master and 6 replicas and some of the parameter group settings. When we commit a code, we have a Jenkins job to run Terraform and automatically create, update, and delete the resources based on your change. By committing this code, Terraform will automatically create 1 Aurora cluster, 1 master instance, 6 replicas, 1 DB parameter group, and 1 DB cluster parameter group automatically for you. It saves us from clicking a lot of buttons on AWS console. Since all the changes are made through code, you can actually track the complete history of the changes in the version control system. Now, after all the Aurora clusters are created using Terraform, the next thing to do is to dump data. We use a tool called MyDumper, which is a faster parallelized MySQL dump. The reason why we do this is because we have many MySQL 5.7 clusters. Creating Aurora replicas through AWS console API was not supported yet. After the data dump is finished, we set up replications from RDS MySQL to Aurora. The next stage is to shift Sleigh traffic from RDS MySQL to Aurora. This is a cheap and low-risk way to get experience of running Aurora in production. We changed the application to send Sleigh traffic to send Sleigh traffic away from MySQL replicas to Aurora replicas, while still sending the master traffic to MySQL masters. The Aurora master is synced with MySQL master with binlog replication. If there's an issue, we can just revert the change without affecting data integrity. We run this setting for our biggest DB clusters for a month. Now the tricky part is how do we migrate the master write traffic with minimum downtime? We came up with a pretty nice solution with the help of DB Proxy. The main benefit of DB Proxy is to decouple the applications from the underlying database infrastructure. We are using a fork of the open source max-scale DB Proxy, including several in-house developed features like configurable connection pooling, request throttling and back pressure, blacklist query rejection, and most importantly, fast connection refresh. I want to highlight fast connection refresh here because it helped us a lot in reducing downtime during the master migration. I will talk about this in a little bit. We deploy DB Proxy in EC2 instances and put it in the middle of the applications and databases. It's the stateless service so that we can scale it horizontally with capacity increase. Now let's take a deeper look at how DB Proxy was set up to realize fast connection refresh. The DB Proxy was configured with 2 connection pools. Each creates persistent connection to MySQL and Aurora respectively. However, only one of the connection pool is active at any given time. The proxy determines which connection pool is active by detecting the current replication topology. It will only activate the pool for the master of the replication topology. The client connections are connected to a DB proxy, and there is a router that routes the client queries to the current active connection pool. When the replication topology changes, the DB proxy quickly detects the change and almost instantaneously route queries to the alternative connection pool. The client doesn't know anything about it, like it's always talking to the same database, because the client connection don't close. It takes only 10 seconds to shift all the queries to the alternative connection pool. The process is extremely fast because the persistent connection were already created, and there is no extra overhead of creating the new connections from the clients. Now let's zoom out a little bit and see how we apply DB Proxy in the master migration. We drop DB Proxy in the middle of application databases. We configure the proxy to manage 2 backends, the MySQL master and Aurora master. The worst thing can happen during migration is losing data. We need to make sure that at any given time, we are making writes to either MySQL or Aurora, but not both. The Aurora team provided us a special store procedure called set read only, which effectively rejects all the writes. First, we write log the MySQL master by setting read only to 1. This will prevent all the writes from the applications, but reads will still be fine. The applications will start seeing write errors from this point. Since there is no write to MySQL master, after we set read only to 1, we wait for the Aurora to catch up replication. And then we reverse the replication, promote Aurora as master and MySQL as Aurora slave. the DB proxy quickly detects the replication topology has changed, and then started to route the master traffic to Aurora. The whole process can be finished under 10 seconds. And then the application will stop seeing write errors. We keep MySQL master write locked to prevent unexpected writes going through. The master migration only creates less than 1 minute of write downtime, and there were no read downtime at all. The MySQL is still synced with Aurora after the migration. We're going to keep this setting for a month. So if any issue comes up, we can revert the migration without losing any data. Once we verify that there is no more errors from the application side, we'll repeat this process for every other clusters. So far, we have migrated 25% of our database clusters, which represents 70% of our total database traffic. Our strategy here is to migrate the biggest and most important clusters to deliver the most impact, and also address the immediate pain point from our team. There are a long tail of 100 plus clusters. They are either internal usages or not serving the core business logic, and we will migrate them gradually in the next few months. Now, conclusion and future work. Here's a quick recap of all the measurable benefits of adopting Aurora. We gained a significant amount of read and write headrooms. We eliminated all the jitters. We have a small and stable replication lag, and we save a lot of time in some of the common database operations. We just started to use Aurora, but haven't really leveraged some of the cool features in Aurora yet. Sometimes we need to run some expensive one-off queries or other crazy things against the real-time data. With Aurora's clone feature, we can quickly spin up a clone instance within 5 minutes, and then delete it after use. Currently, we have some online schema changes that can take hours or days to finish. With fast DDL, I believe it can definitely help a lot in some of the cases. We'll have a requirement to back up data into S3 for disaster recovery. Aurora supports loading data directly into S3, so it will be more convenient than a MySQL dump. So that's the talk. Thank you for joining us.
So hopefully that gave you a good sense of how Airbnb was able to scale their workloads with Aurora and eliminate some of the problems that they were seeing earlier, really getting web scale performance, web scale availability, and also a ton of operational benefit in terms of just all the things that you'd have to do as a DBA. And not just that, but also how they were very methodical about thinking, how do you actually evaluate one of your database targets? And once you made a choice, how do you make sure that you can migrate with as little or no disruption to your web scale workloads? So we're going to stick around. We have a few minutes left still. So please, if you have any questions, find us. Zhenya, Rubong, and I will be here. And thank you again to Zhenya and Rubong for the talk.